Hey, so we're going to do the second part of chapter 15 stuff. And so we're going to be focused on more details about the nature of kind of other galaxies. A lot of the stuff we did in the first part were details that were true to our galaxy, not necessarily true of other galaxies, but a lot of the ideas here are going to be applied to a lot of other galaxies. So what we talked about before, one of the things we talked about before was the disk and the halo and the stars that make up that stuff. And one of the things we saw is that the dynamics of stars in the disk and the halo are pretty different. And it's not just the dynamics, it's actually the stars themselves are really different. So we talk about different stellar populations because we have these two components. They have different sort of dynamics to them, but they also have different properties as far as the stars are concerned. The disk is mostly comprised of objects we call population 1 stars. Population 1 stars are young and metal rich. Okay, so what does that mean? Young in this context means objects that are less than 10 billion years old. Okay, so that's the most exaggerated young you've ever heard, you'll ever hear. But our sun is part of the population 1. It's a young, relatively young star relative to the history of the universe. It's metal rich. What does metal rich mean? In this context, a metal is something that is not hydrogen and helium. Everything else on the periodic table in this context is a metal. So that means carbon and oxygen, nitrogen, things like iron, sodium, all that stuff are all considered iron. And what does rich mean? Well, rich would refer to roughly maybe 3% or so of the star is made up of these heavier elements, where the rest of it is just hydrogen and helium. Okay. Population 2 objects are ones that are primarily found in the halo, in the globular clusters, and just sort of in general in the halo. And these are older stars, older than 10 billion years, and they are relatively metal poor. And metal poor in that context is referring to the fact that they're less than 1% made up of heavy elements. And so there's other sort of distinctions we make here. Population 2 objects, I'm going to kind of just group into one category, just being older than 10 billion years and part of the halo. Although sometimes there's a differentiation made with the bulge, but I'm not going to do that. Population 1, we have intermediate and extreme populations. The extreme means stars that are forming right now. Okay, star-forming regions are the extreme. And intermediate refers to sun-like objects. Okay, so you see in the descriptions here, spiral arms are mostly where the star formation takes place. The entire disk just contains intermediate kind of stars. The extreme have 3% metals, whereas a sun-like star has something around 1 to 2%. And again, the age is anywhere between recently and 10 billion years. That's the idea. So, how do we know this? Well, this is a really important fact about galaxies, is that the fact they contain these different populations. The picture that you see here is a very small section of the sun's spectrum in the ultraviolet. Okay. In fact, this is I think this is the sun actually. The dashed line that you see that runs through here is called the continuum. That is how much light is emitted by the surface of the sun. That's the thermal radiation spectrum level of light. And as you see here, by the time that light gets through the atmosphere and exits the star, it's not at that level. In fact, this is showing all this jagged featured here is showing a lot of absorption lines. So at every wavelength, basically the sun is not emitting its continuum. It's emitting thermal radiation minus all these absorption lines. And some absorption lines are kind of big here and can be identified. But in reality, there are probably thousands of absorption lines that occur in this part of the spectrum. Okay, and the reason why this is because the sun contains a lot of elements that are heavier than hydrogen and helium that can do these absorptions. Okay. This is a classic population 1 star. So we see things like this, we know that we're dealing with intermediate stars. Now, the picture down here is the same. It's the same kind of star like our sun, but it's a population 2 object. This is a halo star. And as you see here, its spectrum, it is mostly emitting its continuum. So the light that's being emitted from the surface mostly does get out. And there's just a few absorption lines here from the same elements that are stated up here. Okay, these are iron and nickel lines. Okay. And this is a very general characteristic we see universally, actually. Older objects have a poor metal content. And the reason for this is an evolutionary reason. At the time that the Milky Way formed, it consisted of mostly hydrogen and helium. This is things made from the Big Bang. And over time, as stars are born and die, they make heavier elements. Carbon, nitrogen, oxygen, things, iron, nickel, all that stuff. And then they die, and they spread that stuff into the interstellar medium, where it's swept up to create a new generation of stars, and they make even more elements, so on and so on. So we see sort of an evolutionary progression with metal content. Things that are very young don't have a lot of heavy elements, and things that are recent do, because they're formed from material that was produced in all these past generations of stars. And so we can make this statement here. Generally speaking, younger stars contain more heavy elements than older stars. Okay. And this is one of many cosmological observations that we make of our galaxy and other galaxies. Okay. That there is an evolution that occurs with the stars. Stars have not always been the same throughout time. Old stars have a poor metal content, and young stars have more metals in them. Okay, is there any questions about that idea? Okay, falls under something we call cosmic nucleosynthesis, how the elements were made in the universe. So this is our general idea, but there are issues with this idea. One of the issues is this. Now, up here, our sun contains in its spectrum iron and nickel. Now, did our sun make that iron and nickel? No, it didn't, right? It will never do that, actually. Our sun does not have the mass to go supernova, which is what you need to be able to make iron and nickel. Iron's only made in the most massive stars. Nickel is actually the element that's made primarily in supernova explosions. It's not something you could normally make. It's heavier than iron, actually. So that means, okay, the iron and nickel that was here and the iron and nickel that exists throughout our solar system was not produced by the sun, was pre-existing the solar system. It had to have been made by some previous star that existed in this area of the galaxy. And when the star exploded, it was able to seed the interstellar medium with all of these elements and elements from its past. And that's what formed the sun. So when you look at this thing here, you have to say the same thing. Well, there's iron and nickel in this. This is a sun-like star. It didn't make these elements. So there is another generation that had to exist before this one. And we term those stars population 3 objects. And these would be the first generation of stars, the ones that start off with just primordial gas, just hydrogen and helium, no other heavy elements because they weren't made yet. And so there's been a lot of search for these stars, and we've not found any of them. And there are many reasons why that could be, but this is sort of a very important thing in astronomy if we're able to discover population 3 stars, basically the first stars. And there could be a lot of reasons for that. One reason is believe that the first generation of stars only formed big. That because of the density of the universe was very high, because it was much smaller in size, that stars like K and M stars wouldn't have formed. So every star that was the first generation is gone now. Other ideas are our galaxy might have formed a bit later than most galaxies, and we've just mixed with stuff that's relatively recent things. Population 3 stars may exist, but not in our galaxy. There's a lot of ideas. But anyway, if this idea is correct, then there should be stars that are only hydrogen helium stars. or there's a very good explanation for why there's not. Okay, so that's a very important idea, and it's something that the future of astronomy will be working on. All right. So anyway, before I leave that idea, questions about that? Okay. So let's look then, since we talked a little bit about the formation, let's talk about the formation of our galaxy. So we envision the formation of our galaxy happening in two different ways. Well, two different ways blended together. There is a traditional sort of scenario for the formation of our galaxy, which would be very alike to how stars form, basically. So we imagine that 12, 13 billion years ago, there's a lot of intergalactic gas, and the intergalactic gas would initially be not necessarily spherical, but it would have some three-dimensional structure to it, and something would trigger it to collapse. So they just estimate in a sphere of some kind. And so that starts to collapse and starts to shrink in size, like the way it happens for stars. And that starts to fragment into pieces as it starts to collapse down to a smaller size. Those bits and pieces would have formed the halo of our galaxy. And the properties of the halo are simply properties that were inherited from this sort of swarm of gas that was in the process of creating our galaxy. So that's kind of consistent with population 2 stars with the halo. Is that the reason why the orbits are so chaotic is because the cloud was originally chaotic. And so bits and pieces break off and they form globular clusters and they form a lot of the stars that are in the halo. And of course, that formed first, so that's why that appears younger. Over time, the structure collapses down to a disk like it does for stars. And what that would do is that would pull most of the dust and gas down into the disk. So the halo is devoid of a lot of that stuff. That's why we don't see it there. Most of the dust and gas gets pulled into here. And because a lot of the dust and gas is pulled into here, you can have star formation happening many, many, many billions of years after the galaxy forms. And so this is sort of the first order idea of how our galaxy and probably every other disk galaxy forms. Halo forms first, and then later on the disk develops. Okay. But there's issues with this, and that's why we have a sort of two different scenarios here. There is probably the real picture of how galaxies are forming is a traditional theory combined with the fact that the Milky Way is going to interact with its neighbors. Because we notice that in our galaxy, we have a lot of odd structure, a lot of apparently mixing of stellar populations, things like that. For example, we believe there's a large ring structure that surrounds the Milky Way galaxy. We have a lot of nearby galaxies that we are sort of connected to. There's like streams of gas, dust, and stars that connect the galaxy's hub. And so it's likely that the traditional process took place and then we interacted with neighbors, collided with things, tidal interactions, tore stars off, even maybe merged together with other things. And so if you combine both those ideas, you come up with probably a pretty good idea of how our galaxy actually came about. The halo also has a wider range of ages than we would expect. I mean, the halo can be anywhere between 10 to 13 billion years old. We expect it to only be within a billion years. And that would make sense if we mixed a lot with our neighbors. So that's the idea. All right. Okay, any ideas about this? Not ideas. I don't want to hear your ideas. Questions? No, just kidding. This is going to be this is actually a big deal in galactic astronomy in general. When we look at any given galaxy, we have a pretty good sense of why the galaxy looks the way it does. In general, 90% of galaxies are disks, like us, or they're elliptical galaxies. And elliptical galaxies is basically, imagine our galaxy with only a halo, no disk at all. It's just gone. And a lot of in fact, most galaxies are structured that way. Only have a halo. They don't have any disks to them at all. And but there is, that said, there's still a lot of, each galaxy is unique. No galaxy looks exactly like another galaxy, so there are effects that happen afterwards. Okay, that's different than stars. A star like our sun, a G2 star, we find another G2 star, it just looks the same. It's just a giant ball of gas. And it probably has some sunspots here and there, but it's the same size, same brightness, same temperature. It's all the same. All right. Great. So now oh, Tyler, you have a question? No, it would simply be a factor of, so if I go back to this traditional picture here, the gas that just happens to be located near the edges would be the gas that kind of gets left behind and clumps together to form things. So at this point, most stars haven't really formed here. This is purely gas. Star formation happens later on. All right, so what we want to do now is this. We want to go back and look at our galaxy and try to figure out what the spiral structure is like. Because we know we're a spiral galaxy, okay? We're a disk galaxy, we have spiral arms, we know that. The picture on the left here is of the Whirlpool galaxy. What we want to be able to do is there some way, even though we live in the disk of the galaxy, we don't have an ability to see a face-on picture, is there some way we could reconstruct how our galaxy might look from a distance? Okay, that's the idea. So when you look at this galaxy here, when you're trying to figure out what the spiral arms look like, when you look at that picture, there are actually two different features that stand out in the spiral arms. Can you tell what those are? The spiral arms compared to like the inner regions of the galaxy, what is different? What's visually different about it? Okay, there's red. Okay, there's a lot of the red color that occurs mainly on the spiral arms, a little bit off of it. That's true. That is star formation. That's interstellar reddening. Okay, the spiral arms are regions where you have a much higher density of stars, dust, and gas. And so because of that, it's more likely that star formation happens there. When the new stars are formed, a lot of them are embedded in their sort of dust cocoons, and so the light, when it's emitted, looks sort of preferentially red. So that's one thing. What's the other thing? You see it? What? It's darker. Yeah. There's more dark nebula along the spiral arms as opposed to inside. That stuff exists in between, but there's a higher concentration of it in the spiral arms. And because of that, that allows us to investigate the disk of our galaxy and look for these features. Okay, we call these tracers of star formation. Tracers of spiral structure. Places where there's a lot of star formation, places where there's a lot of dust and gas, especially dark nebula. If we could map out where that stuff is located, then we could probably reasonably construct a picture of our galaxy. Okay, so the picture on the right here is an attempt to do that with star formation. All the circles here are things called OB associations. Okay, and what OB associations are this? We basically look all along the disk and we look for O stars and B stars. Okay, if we find an O star or a B star, we know, you know now, that they don't live long, right? They live for a very short period of time. In fact, most O stars and B stars will die before the rest of the stars in that cluster form. So it becomes a sort of a perfect way to find the places where star formation is taking place, because these are usually very luminous main sequence stars or supergiants. So they stand out, they're really easy to find. So searching for star formation is a very easy endeavor, actually. All right, so this is sort of one quadrant of our galaxy. And where the sun is located, we have a lot of these OMB associations. Lots of places where OMB stars pop up. Okay. As we look towards the center of our galaxy, this is towards the constellation of Sagittarius, there's a region where there appears to be very little or none, actually. If you go a bit farther, there are more OMB associations. Same deal if you go away. If you go away, There's a region where there's not many, and then there's a band where there's a bunch of them as well. So you're starting to see the same kind of structure you see in this picture for the Whirlpool galaxy. Okay, you see a lot of star formation, a lot of dust and gas, not so much. See more of it here, not so much. So the band structure, sort of on, off, is indicating evidence of some kind of spiral arm there. And so this is easy to do in our quadrant. Other quadrants are a little more challenging because they're further away and you have to look through all the dust and gas to see that stuff. So this is one technique we use. The other technique we use involves the dust and the gas. So all the dark nebulae that you see here, the number one constituent of that is hydrogen. So every place you could find hydrogen gas, you can associate with higher concentrations of dark nebula. And so the question then becomes, well, is there something that hydrogen does that stands out? And it turns out it does. Okay. Hydrogen, neutral hydrogen, meaning like just cold hydrogen in space, can emit a radio wavelength when something special occurs in the atom. The radio wavelength is at 21 centimeters. Okay. So let me explain what's going on there. This picture here on the left shows a standard hydrogen atom, proton, electron. The one on the right shows the same thing. The difference between the two is the electron has a different spin state, we say, compared to the other one. Now, spin that you see here can be thought of as the protons and the electrons physically spinning, but it's an inherent property. It's like charge or it's like mass. These things have an inherent property called spin. And in the hydrogen atom, you can have two configurations. They can spin with their poles in opposite alignment or in the same alignment. Okay? One of these configurations actually has a higher energy than the other one. Okay? The one on the right has a higher energy. It's actually harder to make the spins. Well, here, actually, the spins are in opposite directions, but the polarities are the same. It's kind of like taking two bar magnets, line up side by side. If you do that, they tend to repel each other. Okay, as opposed to taking the two bar magnets and aligning up the opposite polarities, they'll stick together. It's the same idea. In fact, it actually is an identical idea. Okay, so these two polarities repel each other. These two attract each other. So that means this state over here is a higher energy. Okay, by the way, when you do chemistry and you learn about 2 electrons per level, it's because of this. The electron can be spin up or spin down. And that's why you can only fit 2, because you can only have 2 spin states. Anyway, so this one on the right is a higher energy. This one on the left is a lower energy. Now, this is not a common occurrence, but if the hydrogen atom is in this state on the right here, the higher energy state, okay, it has the opportunity to switch to the lower state. The electron will flip its spin, and that's a change in energy, so there's an emission line that's produced. And it's a radio wavelength. Okay, so you learned before about electrons jumping to other levels and producing photons. Well, in fact, there's a lot of other ways to do that. Okay, a molecule can rotate and vibrate, and that produces emission lines, and these spin flips can do it as well. And so hydrogen is the most abundant element in the universe, and these spin flips are pretty common. Now, for a single atom, it takes several millions of years for this to happen. But there is an ungodly large number of hydrogen atoms in the universe. So while this, for a single atom, would take millions of years, there's just so many atoms, our galaxy is flooded with this stuff. So what we do is we search all along the disk at different distances, and we search for this radio signal. And places where the radio signal is the loudest means there must be more hydrogen gas there. So this is basically a probe. We can look through our galaxy, find where this radio emission is taking place, and that's how we know where most of the hydrogen gas is taking place. All right. So you can create a map sort of like this. We look all around our galaxy in the disk, and through Doppler shifts, we can determine distances in addition to their locations. And so we can create maps, and we usually get a picture that looks like this. Now, a picture like this shows the same kind of band structure. You see a lot of gas, not so much. You see a lot of gas, not so much, and so on. That's consistent with how spiral arms look in a galaxy. All right. So this picture here is combining star formation data with radio emission data. And all the places where there's a lot of star formation and a lot of the gas has been indicated here. So all the little dots are places where that's mostly hydrogen gas, and a lot of the blobs that you see here are mostly star formation regions. And so from all the data, we're able to construct an image like this. This is how we sort of envision the data. We're at this galaxy. It's kind of hard to see here, but the center of our galaxy has a bar structure to it. The spiral arms don't start in the middle. They start out from an extended region. It's like literally a bar that's in the middle of the galaxy. It starts from there. And we have 4 major spiral arms: Centaurus, Sagittarius, Perseus, and Cygnus. Those are the major spiral arms. They're large, they're fully connected, but we have a lot of segmented pieces. For example, we live in a segmented arm. We live in what's called the Orion arm. It's not a complete arm. It got broken at some point, but there's other broken arms. There's a broken arm there, and there, and there, and so on. So now the pictures here are images of what our galaxy probably looks like with a little artistic license taken, basically. So we're really ugly. We are. And that's fine. We don't have to look at ourselves, but we're not a very attractive galaxy for a few reasons. Our galaxy shows a lot of signs of tangling with other galaxies in the past. All these segmented arms are the result of interactions we've had with our neighbors. So we don't have this nice, we're not in the calendars, okay, of alien civilizations that don't exist, but anyway. But if they did exist, then they make calendars of galaxies like we do, who knows? We're not in them. Unless they specifically like, I don't know, aesthetics is, right, it's relative. So who knows? I don't know. All right, anyway. But we've noticed a few things that were not evident before. Our spiral arm structure is more complicated than most other galaxies. We have many arms and broken up arms. We have a bar structure in the middle. We actually have this strange ring structure too that's near the middle, and we have ring structures further out. So we got all kinds of things going on. We've seen some stuff. Okay. Any questions about that? Okay, so what I want you to know from this, though, is how we use these two ideas, star formation and the hydrogen gas, as a tracer for spiral arm structure. So now I want to talk about the center of our galaxy. So the center of our galaxy, this is a visual wavelength image of the center of our galaxy. And in particular, what's circled here is the actual center. And doesn't look special at all, right? Now, there is something special going on there, but you can't tell. Why? See? No, it definitely is. Well, it will never reach us, put it that way. Anybody know why we can't? There's some special stuff going on there, but this image is not telling us anything. What's that? Well, yeah, but we can't see it. Why can't we see it? The stuff in front of it. Yeah, visual wavelengths, not a good idea, because it doesn't let you penetrate through the dust and the gas that exist in the galaxy. So this is what William Herschel's trying to do. He's looking towards the center of the galaxy, and there doesn't appear anything special, because in visual wavelengths, there's nothing special. So we can't use visual wavelengths to look towards the center. What should we do? The X-rays would be worse, actually. X-rays are a shorter wavelength of light, and that would be harder, actually, to use. We'll use the infrared. The infrared allows you to look through a lot of the dust and gas, and so this is sort of the same picture, but in the infrared. And when we look at that, there's a couple things we see. First of all, there is a cluster of stars near the center. Okay, that makes sense. If we actually use radio wavelengths here, if we use radio wavelengths, which is even longer wavelengths than infrared, then there is one star that can be seen here, basically. One star. It's called Sagittarius A star. It's located right about there. It's one extremely bright spot. Now, Sagittarius A star means Sagittarius is the direction. A means the brightest radio source in the constellation. And the star means it's not a constant source of radiation. It varies, actually, quite a bit. So if we zoom in on this and we look at the infrared again, we see that cluster of stars. We see that a lot of these stars are kind of young, and the radio source is located right over here where it's labeled. Now, the problem with that is that there's no optical or infrared counterpart to the radio source. Now, a lot of times when we look at sources, we want to see the same source in multiple wavelengths. And when we do, it's usually a result of an object that's very hot. It's thermal radiation. This is not thermal radiation, because if it was, it would show up in the infrared. So this is an extremely strong radio source, but not visible in infrared wavelengths. And the closest we can image it is this right here. Again, nothing there. So back in, I think this was 95, a group at UCLA started to take regular images of the center of the galaxy just to see what the stars were like there. And within just a few years, they noticed that the stars had very high proper motions. They were moving very quickly. And so they kept imaging it. And in some cases, they got complete orbits. But when you look at the orbit of these stars here, what do they look like? They're ellipses, right? I mean, we know this is all Kepler's law stuff. So, I mean, in fact, you look at the paper that releases stuff, it's just the same stuff we did in class. It's Kepler's third law for binaries. Every single one of these stars is treated as a binary star system. There's something in the middle here that doesn't show up in any wavelength. And all these stars appear to be orbiting that point. So we have the distance to this place, around 8 kiloparsecs. You can see the orbits of all these things. So you have all the ingredients that you need for Kepler's third law. And so when we use Kepler's third law to investigate this stuff, we get a combined mass of 3 million solar masses. Now, none of those stars are 3 million solar masses. In fact, you can't have a star that's more than around 120, 150 solar masses. And so these observations, basically this data that you're looking at right here, is the evidence for the existence of a supermassive black hole at the center of our galaxy. It's very massive. Supermassive means millions of solar masses. And it's at the center of our galaxy. And while that sounds really neat, most astronomers say, so what? And that's unfortunately all I can say about this black hole. So what? It's weird that it's there. And astronomers would like to know why it's there. But aside from that, it has no influence over our galaxy in any way. First thing you might notice is none of those stars disappear. So this is a black hole, but as I mentioned before, black holes aren't these vacuum cleaners that they're made out to be. Black holes generally keep stars in stable orbits. Unless you mess with the black hole, you get too close to it, your orbit perturbs in some way. But stars are able to maintain a nice elliptical orbit about this stuff. So that's fine. But it's very odd that something that's millions of solar masses exists here. And so we want to have some explanations for this. But this is millions of solar masses. Our galaxy has billions, hundreds of billions of solar masses. So while this is very massive, it doesn't really control anything outside of its immediate environment. We look at other galaxies and we see that as much as we look, other galaxies have the same thing. They all have supermassive black holes at their centers. This is probably the result of one of two things. When galaxies formed, for whatever reason, there could have been a lot of mass located near their center, and a black hole formed, and it was able to actually sort of swallow up a lot of material that's near the center. It's also believed that this could be a dark matter effect as well. We'll get into this stuff later on, but it's more right now, this is kind of a curious fact more than a crucial aspect of galaxies. And so it's kind of a mystery, but ultimately, if we can't answer this question, it's not a big deal because it doesn't seem to have a lot of importance. But one thing about galactic astronomy right now is we don't have the ability to see the formation of galaxies. It's a technological issue right now. It's just we're not at the point where we have telescopes powerful enough to see that far back in space and time to see the formation of galaxies. That will probably happen in 20, 30, 40 years. But I'm sure once we see that, some of these questions will make more sense. Okay. Any questions about this? Okay, so one of the things I want to mention here is why is there a radio source? Okay, because black holes don't emit light, right? So why would there be a lot of radio source? Well, the radio source, it's actually two things that happen here when they watch this. There's a constant stream of radio waves and occasionally X-ray flares, just a flare of X-rays for a little bit and they turn off. And what's believed happens is this region's filled with interstellar dust and gas. And the dust and gas that orbits the black hole does emit radio waves. It's something called synchrotron emission. It's just when electrons get near magnetic fields, they do these spinny things and they produce radio waves. So a steady stream of electrons are probably flown into the black hole. Not electrons, just gas, dust and gas. And that produces a lot of radio waves. And then occasionally things fall in, apparently. The X-ray flare is probably an object that got close, asteroid, small planet, whatever, and then gets swallowed up. But at the last minute, spews out a bunch of X-rays, goes away. So, but our black hole is dormant. But we're going to talk about galaxies later on. 10% of galaxies don't have dormant black holes. This is dormant, meaning no accretion disk, not actively swallowing up lots of material. But some galaxies do have active ones. And that's kind of crazy because an active black hole in the center of a galaxy usually rivals the brightness of a star in a solar system. So if our black hole was active, we actually would see a lot of visual wavelength emission coming out from this region here. Any questions about this